All right, so that's the kind of the concept we want to start thinking about. Is it's very important to keep track of that. Now, this is the error you make in only one delta t, right? So remember, we're going to iterate. I'm going to solve a system from time 0 to time 1,000,000 or 10 or 100. This error here, what I throw away every step, every delta t I take, I'm throwing away something of order delta t squared. And actually, at the end of the day, what I'm interested in is if I solve it for a long time, what is my error long term? Okay? So there's going to be two types of errors we talk about. Let's call it global error and local error. Okay. So the local error, very easy to get in this case. The local error is local to that time step. How much did I throw away on one single step? Okay? And for this, the more general concept of the local error is to say something like this. My local error, yeah, actually, let me leave it like this. My local error, let's call it little e in a step, is basically going to be defined by the following. Let me explain this. Here is my solution at time k plus 1. Here's my solution at time t of k. What I did here is I said, I'm going to approximate my solution in the future with some routine. Remember, yesterday we said a generic way to represent this is take your solution now, add a little bit of something, and that should get you an approximation to the future. Well, this is your approximation to the future. This is the real future. The difference is the error, okay? Or it's your how far off from reality you are. This kind of almost applies to life, okay? All right, so there you go. That's the local error. How much did I miss the future in one delta t? The global error. Global error is big E, and what we're mostly interested in, which is the following. I choose a time into the future, t of k. This is my exact solution. This is my iterative solution. I just march along, and I get my kth value, and I evaluate it there. So that's my ODE approximation, taking k steps. That's the real thing. And then I say, what's that error? And this is, again, the most important thing. You may be solving a system where you want to evolve it forward into the future, and it's not how much error do I make in a single step. It's a matter of if I run this weather forecast 3 days into the future, you want to understand what's the error 3 days into the future, not 5 minutes maybe is your time step. Who cares about 5 minutes? You're trying to do three-day forecasts or something like that. Okay? So you want to understand how that thing grows. Now, in the context of this simple problem here, it's very easy to understand both concepts, and we can write down exactly how these two things work and how we scale them. Okay? So let's do it for here. We're going to take this simple example here, which we got here, and we're going to calculate local and global error. Okay? So first of all, let's go to the local error, E of k. You just ask the question, what did I throw away? Here is what I threw away. Right? When I did that Taylor's approximation, I threw this term away. That's my error. So my error, and this is where, when we talk about error, we always do order of. We always assume this is just some number. I don't know what it is. Who cares? All I care about is how does it scale with delta t ultimately. 2, there's a factor of 2 there. Who cares? You know, delta. It's all about how does it scale as you change step size. So that's why we use the order symbol. Okay? So that's that. That's the local error. Simple to do for that case. Now let's talk about the global error. What I want to do then is if I make this error every single step, how does that build up? Okay? So the way to think about doing that is just to say, look, let's take an interval of time. I'm going to solve it from time A to time B. Okay, so I'm going to solve it for a period of time. And I'm going to take k steps. Okay? In other words, I'm going to pick delta t times k will be the interval, b minus a. Okay? So is this starting to get low on the board for a lot of you guys back there? Okay. So I'll just write above here. That would joke. Above here, maybe? Yeah, this is hard. I should they should raise me up on a platform. Okay. I'll continue over here then. I usually am pretty good to avoid the bottom. I don't know if you've noticed. You probably didn't quite notice my thoughtfulness to you. That if you notice, I kept everything above here, but since the necks are still going up, I'll go up a little higher. Okay, so I got this k steps. I got a delta t. I got an interval b minus a. So if I look at that thing, what I want to do is for the global error, e sub k, what I've really got here is basically, let me stay consistent with my notes. J equals 1 to k. I have the following formula, which is if every step my error is delta t squared over 2 times the second derivative, evaluate at some c, then I just add them all up. I add up all my error. Okay? Okay, so that's fine. So, but I'm going to make the following observation, that I can basically say, if I take k steps of this, I have k of these. What if I took an average value of the second derivative? So every step I take, this number will change slightly, but I can just sort of take an average value of that second derivative. I don't know what it is. I don't know what these are either. I'm just making this stuff up. So I'm going to take some average value. So really what I'm going to get is delta t squared over 2 times the average value of this. Call it c bar. And I have k of them. Okay? So this is, let's add it up. This is the contribution you get. Now k, by the way, how do I get k? Well, k are my number of steps. So if I come back over here, this is important here. Delta t times k is the interval difference. So you get k is equal to b minus a over delta t. Okay? Simple math. Remember, we're not going to go anything above Taylor expansions. I know, it's surprising. Don't tell anybody. Okay, just tell them I'm in a 580, huge number applied math course. I'm smarter than you. They start with that, and then don't tell them. Don't tell them that I'm like starting below calculus. All right, because there you go. I just did divide, and I put it in here, and you say, okay, if k is that, I will replace that by b minus a over delta t. And here's what's important. I have a delta t here. I have a delta t squared there. And one of them cancels. I know, exactly. I know you guys are in awe of my amazing thinking on my feet. That is what makes me a professor. All right. Now here's the important thing about this formula. How does it scale with delta t? Because that's the one parameter you get to change. This is like order delta t.